Hi everyone, this is my video number 2023, I think. I'm talk on ratio test. Another test that we use to test for the convergence of the series, right? If, for example, the comparison test 1, 2 doesn't work, then we go to the ratio test. So it says that if you have a series given by that, it is a series un for un positive, it means each term of that series is positive, is such that the limit of un plus 1 over un gives some numbers where L is in between, let's say 0 and 1, between 0 and 1, exclude 1, exclude 1, then I think this is not, shouldn't be if, so let un, this series, then this series un converge. Okay, if L, this is L, if L in between 0 and 1, not including 1, for L greater than 1, then this series diverge, I put that way, and if L equal to 1, then no conclusion can be made. No conclusion. So we don't know the series either converge or diverge. Okay, so I'm going to prove this. We know that series converge, or un over n plus 1, we take a limit, this is equal to 1. We let those things, let un limit un plus 1 over un that equal to L, which is L is from 0 to 1. Okay, then by definition of limit, given any epsilon positive, we can find n positive such that the difference between that terms and the limit un plus 1 over un minus L must be less than epsilon. Okay, then if we remove the epsilon, so what we have, un plus 1 un minus L, this is less than epsilon, greater than minus epsilon, right? So that's just a definition of the limit. Now if we take L to the left and right side, so we have un plus 1 over un, this is less than L plus epsilon. We have this on this side is less than L minus epsilon for all n greater than n. Now if I take this right hand side as R, just give a name R, so I can write this un plus 1 over un less than R. We take that. Okay, so bring it out to the other side, so therefore we have un plus 1 less than unr. For for n greater than n. So from there, if I use the n terms and afterwards, okay, the capital N terms and afterwards. So what we have, is that un okay, plus 1, this is less than un r. Okay. And the next term, this is un plus 2, this is less than un plus 1 r. Okay, just use that. And for that, this is less than un is less than un r, so r squared, so we have un r squared. And you can proceed this. We have un plus 3, this is less than un plus 2r, less than un plus 1 r squared, less than un r cubed. So if we proceed this up to, say, n, some numbers, this will give you less than un r to the n, and so on. So therefore, we can write those series un, which is u1 plus u2 plus u3 plus, and so on, up to un plus 1, right, un plus 2, and so on, un plus 2, and so on. Okay, since each of this un is same as un, and un plus 1 is less than un r squared, un plus 2, un plus 1 is less than un r, right, un plus 2 less than un r squared, and so on. So what we have, this is less than u1 plus u2 plus u3 plus. Okay, for that you have un, for that we have un r, for that we have un r squared, and so on. Okay, so for this part here, you can factor out un, because you have everything un there. So that u1 plus u2 plus you can factor out un. Then inside there you have 1 plus r squared plus, and so on. And what is this? This is, if you sum up those, this is 1 over 1 minus r. So altogether there, so you have u1 plus u2 plus un 1 over 1 minus r. For r less than 1, greater than 0. So if you look at this, definitely u1 plus u2 plus un minus 1 give you some numbers. This part converge. Alright, for r between 0 and 1, so definitely that one is converged. So basically everything is converged. So therefore this series un converge. So that's a proof. Okay, so we go to the next we go to the example, but let me stress again the limit. We want to test the limit for we want to test the convergence for the un, for the series un. So we take a limit un plus 1 over un, and if this limit equal to L, where L between 0 and 1, okay, then that series converge. Okay, if L greater than 1, then that series diverge. And if L equal to 1, then no conclusion. No conclusion can be made. So which means we don't know the behavior of the given series. Now let's look at some example of how to apply this ratio test. First example, so let's consider this series 3 to power n factorial. Okay, so if you take a limit of this is un. Okay, this is un. Now if you take a limit un plus 1 over un, so what we have, n goes to infinity. So what we have here is that un plus 1 is 3 n plus 1 over n plus 1 factorial. Okay, un, so you just inverse that one, n factorial over 3 over n. So from there you can write this is 3, so we have 3n times 3, you have n factorial there, down there n plus 1 factorial is n plus 1 times n factorial, so we have 3n. Okay, so that you can cancel out, that you can cancel out, that you can cancel out, that, oh sorry, missing limit here, limit n goes to infinity, n goes to infinity. So we have limit n goes to infinity. What left? 3 over n plus 1. Okay, you take the limit of this thing, you take the limit of this thing, that give you 0, and this 0 is definitely less than 1, so therefore you can make it you can make a conclusion that the given series 3n over n factorial is convergence. Another example, the summation of series of 3n over n squared. Okay, we take a limit un plus 1, 3 n plus 1 over n plus 1 squared, n plus 1 squared, un plus 1 over un, so we have n squared over 3n. Okay, so what left is that n infinity, that definitely you can split those things, 3n over times 3, that you can cancel out. So what left is n 3n squared over, you can factor out those things, open the bracket, so you have n squared plus 2n plus 1. If you take a limit of this is equal to 3, then this is greater than 1. Okay, so therefore that series over n squared diverge. Pretty easy, isn't it? Okay, one more example. There's 1, 2, 3. Summation of series of n squared, n over n over n factorial. Okay, so we take a limit n goes to infinity. Un plus 1, so we have n plus 1 over n plus 1 factorial divided by un, so we have n factorial over n to the power n. Okay, so what we have here, limit n goes to infinity. That one you can take out n plus 1. Okay, so we have n plus 1 or 1 plus n to the n. We have another n plus 1. Okay, we have n factorial over, for that we have n plus 1 factorial, so n plus 1 times n factorial n to the n. Okay, so that this cancel out, that cancel out, that cancel out. So what left is that this is limit n goes to infinity, so we have n plus 1 to the n over n plus n to the n. So you can simplify this. This is limit n goes to infinity. This is n plus 1 over n to the n. And this limit n goes to infinity. I can do this because the power is same. Okay. From there I can write this as this is 1 plus 1 over n to the power of n. I think you can recognize this series. This give you, we take a limit 1 plus 1 over n to the n, that give you e, isn't it? If you remember, e, and this is the definitely e is greater than 1 because e is 2 point something, 2.7 something. Alright, so therefore we can conclude that the series that we want to test is diverge. N to the n over n factorial, this is diverge. I have one more example, but I would like you to try it out. Okay, this is not difficult. It's not difficult. You try this. Sum n factorial squared over 2n factorial. Okay, I'll give you hints for this. N infinity un plus 1 over un, that will give you 1 over 4. The rest you do it, and this series converge. Okay, it's converge. Less than 1, so the series converge. Okay, so next I give a ratio test. No, integral test. Integral test. Alright. So what is integral test? Let f be a monotonically decreasing for positive real function. Monotonically decreasing positive real function. Positive real function with the property that fn is equal to un for n 1, 2, 3, and so on. Okay, so if integrate from 1 to infinity fx dx converge, then this series un converge. If it diverge, if those diverge 1 to infinity fx dx, if that diverge, then that un diverge. Okay, so those integral 1 to infinity fx dx is just the same meaning as if you take a limit n goes to infinity, integrate 1 to n fx dx. It's just the same meaning. Alright, so let's prove this. Let's prove this theorem. Okay, so let fn is equal to un for n 1, 2, 3, and so on, be a monotonically decreasing function, then for any integer r, for r integer, so we have fx is basically in between ur plus 1. Now you can do this because f is a function, fx is a function, so function you can determine for any x. So and ur plus 1 is less than ur because the function is decreasing, so I can write this. So where x in between r and r plus 1. So if you integrate this over the interval, integrate over the interval r plus 1. So what we have, u r plus 1 is less than, we integrate this function from 0 to from r to r plus 1 fx dx, that will be less than ur. Okay, remember that u is a terms, so if you have, for example, this is r is here, this is r plus 1 is here, then ur is somewhere here, this is ur, this is ur plus 1, so we consider a function between ur and ur plus 1. Probably that function look like something like that, we don't know, but surely in between ur plus 1 and r plus 1, and as well as for x between r and r plus 1. Okay, then from there we have then this, if we take a series for r equal to 1 and ur plus 1, this is just the same as ur r equal to 2 to n plus 1. Alright, so this is less than, because we are less than, we take a summation, r equal to 1 to n, we integrate r to r plus 1 fx dx. This is less than sum r from 1 to n ur. ur. So we have those. Okay. So what we have now is that u and r is that series or the summation of those less than u and ur for r equal to 2, or less than those r ur plus 1 for r equal to 1. Yeah. Okay, and that one less than ur and r from 1 to n. So I can write this, just take that part, so I can write this as a sum of un, so ur r from 2 to n plus 1 less than integrate 1 n plus 1 fx dx. This is less than sum ur r equal to 1 to n. Okay, so if you take Sn as a partial series of sum un, so if you let Sn is u1 plus u2 plus the partial sum of un, so you can see from that, because this is n from 2, so I can remove those s1, I can put it, not remove it, put it in the right hand side, left hand side, so Sn minus u1 equal to u2 plus that, really give you that. Okay, so those inequality becomes Sn Sr up to n, so n plus 1, Sn plus 1 minus u1 less than integrate 1 to n plus 1 fx dx, that less than those Sr. Then from here we can use the a comparison test. Okay, comparison test. If the bigger series converge, the smaller series converge. Okay, if the smaller series diverge, then the bigger series diverge. So let's end up our proof. So I put the conclusion here. I put the conclusion. If we take a limit, n goes to infinity, integrate 1 to n plus 1 fx dx. Okay, if this series diverge, if that series diverge, if this series diverge, if the smaller series diverge, the bigger series diverge. So we have Sn or Sr diverge. Okay, if the smaller series diverge, the bigger series diverge. And if the limit n goes to infinity, integrate n plus 1 fx dx, if that one converge, okay, you look at the left part, if that one converge, if the bigger series converge, the smaller series also converge. This is just a number, so don't worry. So we have SR converge. Okay, so that's the end of the proof. Now let me describe some example. First, let's see this series. We haven't tested this series, so let's do it now. Okay. All this while, we know that the series 1 over n squared is converged. Now, let's prove this series converge. Using the integral test, we let fx or fn is equal to 1 over n squared. So I can have fx equal to 1 over x squared. So therefore, I take we integrate this thing from 1 to infinity, basically, n to infinity, or you can also write n goes to infinity. This is n. You can also write like that. Fx dx, that limit n goes to infinity, integrate 1 to n. That 1 over x squared dx, that give you limit n infinity 1 over x squared, so we have 1 minus 1 over x, alright, from 1 to n, alright, so that what we have, limit n goes to infinity, so we have minus there, I can bring it there outside, so then 1 over x, so we have 1 over n minus 1 over 1, minus 1. Okay, you take a limit, that one goes to 0, so that give you 1. Right? So which means that series converge. Okay. Can you try this one? What about this one? 1 over 2 to the n. Again, we let fn 1 over 2 to the n. So we take a limit of those things. N goes to infinity, integrate 1 to n. 1 over 2 to the x dx. Now how to integrate this? I think I just leave it to you. Is it okay? Let me give you hints. For that, we substitute, let's say, y equal to 1 over 2 to the x. Okay, let's take that. So this is equal to 2 to the minus x. Yeah, same thing, right? Take a ln or log a ln for both sides. So we have ln y that equal to minus x ln 2. Okay. Then from there we need to substitute dx here. So you need to find what dx is. You differentiate both sides. So this is, you got 1 over y dy that equal to minus ln 2 dx. That from this we have dx is equal to negative 1 over y ln 2 dy. Okay, then from there you can just substitute. So that limit n goes to infinity, integrate those one, n 1 over 2x, 1 over 2x is y, that's y, dx is this, so we have negative 1 over y ln 2 dy. Okay, then you just need to cancel out that. This is just a constant, so that gives you negative 1 over ln 2. Okay, limit n goes to infinity, 1 to n dy. So dy, you got y. From 1 to n. And substitute this y into that. Then you will find that this series, you will find that series 1 over 2n converge. You do the rest. Okay, just leave up to that, and then you do the rest. Okay, so in this video, what I did, I proved the, I give you the ratio test, and I give the proof of the ratio test, as well as the integral test, the proof of the integral test, and some example of the integral test. So I think I stop there for this video. We continue to the next. Thank you.